I'm Guang Tan from Chinese Academy of Sciences, based in Shenzhen. Today I'm going to present our recent work on the indoor positioning system. This work is done in collaboration with Bo Xie and He Tian. So our system called SpinLight uses light signal for the positioning. The main features that distinguish it from previous systems are its high accuracy and robustness. When we say high accuracy, we want that the distance error to be within 10 centimeters most of the time. This level of accuracy benefits many emerging applications. For example, in the area of robots or automated guided vehicles, these machines can be made to move along planned routes. Or on a parcel sorting or assembly line, the objects can be tracked or manipulated with high precision. The accuracy can also be very useful for small object search in, for instance, a library or in a supermarket. The location information has been proved to be very helpful in improving gaming experience and improving the quality of entertainment. Here are a list of recent systems that provide sub-meter accuracy. There aren't many systems that really provide sub-decimeter level accuracy, but still we can make a comparison. So basically, there are two approaches to achieving high accuracy. The first approach is light signal. The advantage of this approach is that the signal propagation is highly predictable. This allows us to establish a very accurate location model. The obvious limitation is that the line of sight dependence, of course. In contrast, the RF approach works for non-line of sight environments, but signal propagation is known to be very indeterministical. So this causes troubles when we are pursuing high accuracy. So, for example, there's two RFID systems, Tigram or Pinit. They both provide accuracy to about 10 centimeters. But the first system requires the object to be mobile so that the system can connect a lot of measurements to narrow down the area of the object. Or in the Pinit, a very high dense deployment of reference tags are needed. Okay? So these two approaches are very complementary. The highlight of SpinLight is its accuracy. On average, the error is about 4 centimeters. It is also robust against environmental factors because it uses a digital design. Now, where do we get this basic idea of the design? So we have all been in this disco ball room. There is this disco ball light that rotates along the two axes. Along with the power control of the light, these are the different light beams created that move around in the air. Also, there are these spotlight shadows in different colors that also move around on the ground. We observe that these light spots actually convey very rich information for localization. Okay, that's the start point of our system design. So the basic framework is like this. We have here, this is the transmitter of our system. This transmitter, apart from this LED light chip, the key component is this light shade. The light shade, we have opened some seals on the shade to allow the light to pass through. This creates some light beams. Okay. We use the light beams to divide the space into spatial beams. So what the receiver needs to do is to find out which light beam, which spatial beam it is located in, by detecting and analyzing the light signal it receives. There's no need for RSS-based ranging. Okay. Let's take a close look at the shade, which is key to our system design. The shade is divided into cells. Some cells are open to allow the light to pass through. Some some other cells block the light. So this gives us zeros and ones. Okay, there are different rings. Each ring is coded in different way, so we can help the receiver identify which ring it is located in. So in reality, we do not want this visible disturbance from this moving light beams, so we can use infrared for the localization. This picture is a projection of the shade onto the ground. Okay, it's actually a polar coordinate system. There is an initial direction defined arbitrarily. Also, there is a start point on the shade. When the start point hits the initial direction, we have this aligned coordinate system. So the receiver here, represented by this red dot, it needs to find out its ring number in the radial direction, also the cell number. Okay. So how do we create the flash patterns and make the light beams move around? This is an illustration of our transmitter. There is a base plane that contains a light chip, and this light shade is rotated by a step motor, which is further controlled by a microcontroller. Each transmitter uses 2 flash frequencies. These are used to synchronize with the receiver when the new rotation starts. Here we used an opto-isolator sensor. Here, when this barrier on the shade passes through the U-shaped this sensor, the infrared, there's an infrared between the 2 walls will be blocked and the signal will be triggered so that MCU will instruct the light to flash at another frequency. Okay. Here is a picture of our transmitter. This transmitter has a base plane. This framework is actually taken from a real disco ball light. In the middle of the plane is the step motor with a light chip. And this cover is made by a 3D printer. Okay. Some of the blocks can be covered to simulate 0 cells. Okay. This is an example of the coded shade. There are 8 rings. In each ring, there is a preamble. Okay. It's just a sequence of 1 cells. And this ring ID parts is a 2-level coding scheme. On the high level, the high level we use what we call microbits. For example, a micro 1 is represented by some 5 regular bits, 11110, and a micro 0 by 11101. We use this 2-level coding for some special purposes such as location optimization and fault tolerance. And lastly, we have this extension bit part. It contains a special cell that helps improve the accuracy. This will be covered shortly. Now, the design is much simpler at the receiver side. The receiver simply consists of a light sensor, a microcontroller, and a communication module. Okay, we can see the light signal. Okay, in time and the frequency domains, this can be better seen in this spectrogram of the signal. We can see 3 frequency components. The 100 Hertz is from the fluorescent lamps, which can be easily removed. And then we have 2 frequencies that are used by the transmitter. Okay. The sequence of this light spots represent the ring code. Okay. What the receiver needs to do is to decode the signal. There is a switch point. A switch point helps the receiver to determine. Okay. To determine when a new rotation starts. Okay, so from this time on, it can start to count the number of cells passing by, so as to estimate its angular offset with respect to the initial direction. Now we have the ring number and the cell number. Okay, this is enough to give us a rough estimate of the location, but it is not accurate enough, because just imagine how a small cell is projected to a far distance on the ground. This cell will be enlarged to, for example, a half-meter size. So this is not satisfactory enough. We still need to obtain two offsets, an angular offset and a radial offset within the cell. Okay. The angular offset delta theta is relatively easy to obtain. Just look at this in the picture of the signal. We can see normally a bright spot has a width that is a unit width that corresponds to the angular span of a cell. Okay, because the rotation speed is constant. But for some special cases, there is a light spot in the beginning of the sequence that has width of only a fraction of the cell period. This fraction, the width of this fraction is proportional to the angular span. So from the width of this very narrow light spot, we can estimate delta theta. Okay. Now delta R is more complicated. The problem with delta R is that at different locations in the radial direction, the receiver will see the same length of signal window, because this, for example, these two curves have the same angular span. Okay, that means at these two locations, the receiver will receive the same number of signal samples. What we do is to break this homogeneity with a special cell in the extension bits part. This special cell is something between a 1 cell and a 0 cell. It can be sort of as an open cell partially covered or a closed cell partially opened. Okay, it's in a triangular shape. What it does is to give us variousness of signal window for different delta R. Okay, here we see these two curves, the red one and the blue one, now have different angular spans. So it means they will receive different lengths of the signal window. This is a measurement of the relationship between delta R and the angular span in time. You can see this relationship is very predictable. Actually, the curve can be obtained analytically with some geometrical analysis, because all the angles and the edge lengths are known. Okay. Now, the knowledge of delta theta and delta R helps us to narrow down the possible area of the receiver to a few centimeters. We have achieved our goal of high accuracy. Apart from this goal, we also want the system to be reliable. This is especially important for a digital system. Okay. Now we have considered a major type of error that may occur in the system. This is caused by the LED chip. So in reality, a chip is quite small, just the size as a thumbnail, but it still has a size. The size will manifest itself at a certain distance on the ground. It will create some gray bands between the cells. That means these cell edges will become blurry. This will confuse the receiver as to which side it is located in. If it gets a wrong ring number, it will get a wrong location. And this is what we want to avoid. Okay. Now we have examined the possible situations where this error may occur. So depending on the intensity threshold for a 0-1 judgment, there are only two possible cases. The first is erroneous radiance 00 or double 1. Okay. So what do we do with this 00 or 1? Let's first look at the case of 00. With our coding rules, 00 is forbidden in the ring ID part. it never appears in the ring ID coding, okay? So when this is detected, then the receiver will know that the microbit must have gone wrong, okay? Also, with the help of the triangular cell, the receiver will know that it is near the border between two neighboring rings. So with the help of the coding rules and triangular cells, it is able to recognize the errors. So let's examine the possible cases of two neighboring rings, K to K plus 1. There are 3 cases for this, bit flip, okay? For example, this bit flip will be detected by finding out this 00 regular bits. These are all microbits. So this, in those 3 cases, the red microbits can be detected and corrected. Okay? So along with normal microbits, the true ring ID can be recovered. Okay. So far, we have looked at only the 2D plane on the ground. So still, the height of the receiver is unknown. So in order to obtain a full 3D location, we need two transmitters. Each transmitter gives us an array for the receiver's location, and 2 rays intersect to give us 3D locations. This is an example of the signal. There are 4 frequencies from the 2 transmitters. Okay. All right, here are some pictures of our prototypes implementation. Here we can see a transmitter projecting the light onto the wall. Okay. There are light beams rotating in the air. We use the 3-watt LED in the system. It covers about 95 square meters when it is placed 3 meters apart from the wall. Okay. This is a light sensor that picks up the signal for processing the microcontroller. Here are some examples of the shade design from the 3D Max software. Actually, there are many ways to code the shade. These are some simple examples. What might be interesting here is the triangular cells, which we use to refine the location and help with fault tolerance. Okay. The edges between this, see, this is front face of the shade. There are edges in our final product printed by a 3D printer. These edges are removed because this creates some extra shadows on the ground. Okay, this is for just for experiments. This is one of the final shapes we used for the product. Let's first look at the performance in accuracy. We compared SpinLight with several RSS-based systems. In particular, Epsilon, which uses a well-known light intensity model for positioning. On average, it provides a distance error about 4 centimeters. And most of the time, the error is within 7 centimeters. Okay. This is an order of magnitude improvement compared with this RSS-based systems. For example, the Epsilon, they have an average error about 40 centimeters. This is consistent with the results in the original literature. Okay. We also look at this impact of distance on the performance. When distance increases, the noise to signal ratio will increase. This will cause trouble to the analog systems because there is more noise and the distance estimate becomes inaccurate. But we can say that the accuracy remains very stable for SpinLight. This is because it uses a binary decision as to the existence of a light signal. So a moderate increase of noise does not bring any difference to the performance. This obvious difference for other systems when the distance increase. Okay. Reflection, we place different materials near the receiver to create this light reflection. Only when there is a ceramic tier near the receiver, we can see a slight increase of error for SpinLight. For other systems, the impact is very obvious. Then we examine the impact of orientation of the receiver. For RSS-based systems, the orientation is a critical factor in the location model because the instant angle has a great impact on the light intensity sensed by the receiver. So in those systems, either they use actual sensor to correct the angle, or they require the user to cooperate. For instance, by keeping the receiver horizontal in order to solve for a unique position. This is not needed in SpinLight, again, thanks to the binary judgment of light signal. This makes SpinLight more flexible in some application scenarios. Finally, the impact of ambient lights is quite small. Let me summarize the talk. SpinLight is a digital positioning system that provides much improved accuracy than analog systems. It is robust against environmental factors, most of the factors we can envision in reality. Okay. An additional merit is that this receiver is very low power. This makes it possible to realize a tag-like receiver, and so such applications, a tag is expected to run for months or years with a small cell battery. Okay, this is impossible for like a camera sensor or a Wi-Fi module. Future work, an interesting topic would be how to remedy the limitation of an unknown site. This is actually a grand challenge for light positioning. We are looking at the ways of combining RF with light signal. So when the unknown site is available, or the positioning will be done as usual. When it is lost, the radio patterns recorded previously can be used for a location estimate or approximation. We also will investigate more fault tolerance issues, such as those caused by mechanical inaccuracies. Okay. We also would like a smaller localization delay. Currently, the delay is up to 2 seconds. Okay. This may not be enough for real-time applications. This is the talk. Thank you for your time. Questions?